Hello everyone, my name is Dmitry and I'm from St. Petersburg State University, and today I will present the work closely related to printed circuit boards production. Shortly it's called PCBs and I'll talk about that. Our plan is, firstly, I will say some words about the standard methods of PCBs production. After that we will talk about the one specific method of deposition of metals onto the electrics. It's laser liquid phase deposition. And after that, in the rest part, I will talk about the theoretical mechanism of this phenomena. So let's start. Let's start from the standard photomask and photolithography method of PCBs production, which consists of several stages. For example, ultraviolet irradiation of special photosensitive organic layer that's going on right now. After that, after irradiation, we need to check the quality of our work here. And the next stage is washing. We need to wash our plate, our matrix, our dielectrics from the organic layer. Unreacted, we need to remove unreacted or reacted parts of this photosensitive organic layer by using special chemical solution. And after that, we will wash our plates by pure water. So this method generally is very precise, but it has several disadvantages. For example, it has many steps, it takes a longer time, and it requires a quite expensive equipment. And for small series of PCBs production of a small series of PCBs, for this aim, some other methods have been developed. For example, two-dimensional, three-dimensional printing by using special conductive ink based on silver nanoparticles, tin lead nanoparticles, any metal nanoparticles. This method allows us to get multi-stage printed circuit boards as shown on the screen. So it's a positive method where we apply the new conductors onto the electrics. There are different methods. It's negative methods where we need to remove some parts of the copper film, for example, from the dielectric surface. For example, it's etching, mechanical etching. It's a quite old and very cheap method of individual PCBs production, but also it takes a lot of time. For example, for two double-sided printed circuit boards we need to take around 1 hour. We need to spend around 1 hour. Also we can use laser, powerful infrared or ultraviolet laser to remove copper film from the dielectric. But there is one question, it's a very fast method, but there is one question to this method about energy efficiency. And also, as we can see on this video, we need to use very thin foil, very thin copper film to use this method successfully and to do it successfully. So on this point, on this note, I'd like to finish my introduction, and here's the first part of my presentation is closed. I just tried to say that there are many different methods of PCBs production, but in the rest part, for the mass scale, for small scale, for individual production, but in the rest part of the presentation I'll talk just about one specific method of deposition. It's laser-induced chemical liquid phase deposition on the example of copper. Shortly it's called LCLD, and I will use this abbreviation. It's a non-standard, unusual method of applying of metals, conductors onto the electrics, and this is one-pot method where the creation topology and creation of conductors, nanoparticles, accompany to creation topology. So on this slide I will explain the key idea of this method. This method is very similar to laser etching, but in the laser etching we are removing material. In the laser liquid phase deposition we are adding material, and we are forming the metal onto the electrics in the laser focus by using special chemical reaction in the water solution, in the water chemical solution consisting of two parts, reducing agent and oxidizer. It's usually metal salt. So the chemical reaction takes place exactly in the laser focus. Let's look at our equipment. It's a very simple scheme. We use just very cheap DPSS laser, 532 nanometers. After that, the laser beam is going to the focusing lens system of optical microscope, and after that, the laser beam is focusing on the interface between the liquid solution and solid dielectric substrate in the mobile cuvette. And here we can see the result. It's one of the deposited track deposited by LCLD. It's a copper track, red copper track, and here on this part we can see quite good normal topology. But here is round-shaped defects, round-shaped empty zones. It's a defects. Also, please pay attention on half-round topology of all the track. Half-round, and half-round. Also, please note the presence of many small bright balls everywhere in the surface of this track. Bright balls, it's a melted copper. It means that in the center of the track, in the center of the focal zone, in the laser focal zone, we have to deal with very high temperature. That's higher than 1100 degrees of Celsius. That's higher than melting point of copper. So that's the reason why under deposited material we can observe the total thermal destruction of dielectric substrate and many thermal splits like here, and here. Those all defects, it's thermal splitting due to presence of great temperature gradient near to the laser focus. So also in the center of the track, in the central axis, we can observe quite often. We can observe the traces of melted ceramics. So the presence of high temperature zone in the center of the track speaks us about presence of film bowling zone in the center of the track and in the laser focus. Because the film bowling mode, it's a just sole variant of equilibrium between the quite cold liquid in the bulk solution. The temperature is around 25 degrees of Celsius, and very hot steel spheres. For example, on the example of two steel spheres in the pure water, like here, like on this video. So on the left part we see the transition between film bowling and bubble bowling, but on the right picture we have dealt just only with film bowling. So absolutely same situation. The Leidenfrost, it's a well-known Leidenfrost effect, film bowling mode in the liquid solution, and with this effect we have deal in LCLD. So it's a key idea of my of the second part of my presentation. Before we start to talk about the mechanism of this effect, I would like to say some words about the history. Several years ago we planned to use laser-induced liquid phase deposition to real production of printed circuit boards in the small scale. But unfortunately it was impossible due to the thermal decomposition of the dielectric substrate and due to presence of many defects in the structure of the tracks. So it was impossible, but we noticed that this effect is it's a very interesting method from the theoretical point of view, because despite of the fact that laser etching, laser cutting, laser drilling, laser ablation, mechanical etching, two-dimensional, three-dimensional printing, and other processes, like you can see here, all of these processes are very well studied methods, processes, and technologies. At the same time, the interaction between the powerful laser light, especially focused, and with chemically active substrate, chemically active liquid solution, was almost unknown and was almost unstudied at that time. So this study and this work, it's a pure theoretical investigation of the interaction between the powerful light and the chemically active liquid. So, and let's consider the mechanism of this interaction step by step. Firstly, we need to initiate the reaction by steel knead. After that, the small bubble appears and it's growing up, and gas bubble growing up and filling it by water vapor. Also, in the center of the track, in the center of the gas bubble, the temperature also is growing up, and we come to the film bowling mode and to the heat transfer effects in liquids and substrate. And after that, the mobile cuvette for deposition is moving. And now we need to take into account one additional effect. It's thermal netness of the dielectric substrate. Due to this effect, the maximum point of the temperature inside of the solid state, inside of the solid dielectric, is shifted back to the back edge of main reaction spot. And this is first reaction zone, where the chemical reaction takes place. And source of energy for this chemical reaction is exactly the shifted back maximum of temperature in the solid dielectric due to its thermal netness. So this is first reaction zone, but there is a different zone, second one zone. It's a front edge. It's a front edge of the main gas bubbles, where the reaction also takes place, because the energy, the source of energy for this reaction it's exactly the laser power that ahead of movement of the main volume of the gas bubbles here. So there is just only two zones of chemical reactions. It's a front edge and back edge, and all chemical reaction with forming of metal takes place only on those two edges that lead to formation of so-called half-round topology. Half-round topology of the track. And there are many tracks with half-round topology, where we can prove this hypothesis, where we can find the evidence for this hypothesis. For example, on the example of this track, half round and full round topology. Let's make a zoom. Let's make a zoom, and we will see that everywhere we can see the half round traces of metals, half round curves. Everywhere we see half round topology. So by this, according to this mechanism, the deposition takes place only on the edges, front edge, back edge. But there is a different mechanism where deposition can be observed exactly in the center of the laser spot, exactly in the center of the laser focus. It's so-called rain metal mechanism. So rain is coming. Middle rain is coming, and soon I'll explain this mechanism. But firstly, let's look at the one of the wall track, and exactly let's look at the center of this track, where we can observe very homogeneous coatings of spherical nanoparticles. Everywhere we see spherical nanoparticles, nanoballs with diameter around 80 nanometers. 80 nanometers. How is it forming? It's a classical monolayer of nanoparticles. How is it forming? This is my question. Soon I will explain that. Let's look at the right part of this movie. It's a evaporation of salt water, where the salt films forms on the borderline between the air and salt solution. Absolutely same effect we can observe in the case of laser-induced liquid phase deposition, where we can deal with chemical solution consisting of non-volatile and volatile components. Non-volatile, it's for example metal salts, copper sulfate, copper chlorate, and other salts. So here we have deal with salt film of non-volatile components of this chemical solution. After the forming, when the salts crystallize on this borderline, this film of salts can be broken down into small particles and fall into the heated gas phase. Like shown on this animation, and on this animation too. It's metal rain, because the particles in the heated vapor under the action of laser radiation, they are heating there, melting there, and reacting there, and forming small balls, small drops of liquid metal. And by this way, those particles form of nanocoatings and homogeneous monolayers of nanoparticles. Okay. And there are many tracks consisting entirely of sprayed nanoparticles. For example, this is one of them. It's a track formed by LCLD with around 56-55 micrometers, and with very homogeneous surface consisting of spheric nanoparticles, nanoballs with diameter around 120 and 140 nanometers. So after that we cracked the sample to investigate it more attentively. And after that we can see the cross-sectional view. We will see cross-sectional view of this track with, and we can measure the thickness.